Okay, so we start with the segment, the example 9.1. And as we are just saying about that uncompensated portion, we already discussed that, and we figured out our steady state error of the uncompensated one. And we want is to have zero steady state error, and for that we need active components, ideal compensator or PI controller. And this portion is arbitrarily been selected. So what we know so far is we have to pick a pole at the origin. So we are picking a pole at the origin. So this is what you have to take. And in addition, because that we don't want to change or reshape our root locus, because we are actually happy with our transient behavior, we actually have to have a nearby zero. Okay, so we have to have a nearby zero. So this portion is arbitrary. So where you are choosing your zero location is arbitrary, but it is better to choose a nearby one. So we are choosing arbitrarily at location minus 0.1. So we are going to see how it behaves. So based on that, actually, you can take some other approximation as well, like say 0.01, 0.001. The closer, the better. The bottom line is we have to have a pole at the origin and a very nearby zero, so that the effect of the angle contribution of the pole at the origin can be cancelled, and we are almost at the previous location of our root locus. Okay, so the next question is what now? What will be your block diagram? How the block diagram should look like? Okay, so the block diagram should look something like this. Just add that extra additional compensator. Additional compensator. Okay, so S plus 0.1 divided by S, and also we have our gain controller. So even though it is not that necessary, the gate controller, we already figured out the magnitude, which was in the last case 164.588 approximately. So this is the last. So what you have to check is whether this one is also changing or not. So this is also one of the observations that we have to make. And then don't forget the plant. So you have the plant itself, GPS, which is the same one as before. So this is our modified diagram. So we are interested about the question that is whether we actually have to plot it again or not. So now let us just calculate the steady state error. We know that we have introduced a system type. So now you have forward path gain. Okay, you can just give F for forward path gain to avoid confusion about kg of s, h of s. So you can also write something like that. So s plus k times s plus 0.1 divided by s plus 1, s plus 2, and s plus 10. So I was actually dealing with this previous control system, the system. Okay, so as you can see here, this time, if you go give a step input, so if you are still about to figure out the KP, okay, step response, then it will be having limit s tends to 0, GFS. So basically it will be infinity, because 1 by 0 is infinity. And then your steady state error is going to be 1 by 1 plus infinity, that is 0. So this is our objective, which is fulfilled. Now the next question is, with this objective, with this inclusion of these two, pole and zero, so do we have to plot the root locus again or not? Okay, so let us try to answer this in MATLAB, and let us see how much it is going to vary. Okay, so yeah, I think you can see here two systems we have. The first portion here is actually uncompensated one, compensated system. We figured out the numerator, denominator, then we figured out our uh, G of S. Okay, so with the G of S, we actually we avoided that 164.588. Okay, and using that this one, we actually have to plot the root locus. So this is useful for the plotting the root locus, but we are also interested to see the final result. So for the final result, we applied the unity feedback. Then for the unity feedback, you have to include the gain. Okay, similar thing we have done for the compensated one. I already know the gain will be changed a bit, and it will be approximately 158.2 according to the book. So that is why for the compensated system closed loop transfer function, I changed it already. But this is also what we are going to see from the root locus, that how they are actually changing. So let us go and see about the root locus, how they're changing. Okay, so now if we plot it, okay, so if we plot it, then let's go to the image. Okay, so look at here. Okay, so almost identical. One root locus is actually on top of the other, so it's very difficult to see how much they are varying. And I also have drawn one line, that is your zeta line. Okay, so the black line that is basically your zeta line. So from this uh, actual drawing, it's very difficult to see, but you can also zoom it, and then actually you can see how much they are actually deviating. So let us zoom it, zoom this segment, then you're going to see how much they're actually changing. Okay, so very negligible changes. So the question whether you should plot the root locus again after adjusting the steady state error, it is actually pointless because of the fact you are going to do it by hand. So by hand, this negligible change will not be uh, uh, distinguishable. So that is why it is not necessary for you to draw it again. Now, what about the changes in the gain? So for finding the changes in the gain, there is another instruction that you have to write, that is rlog find. Okay, so if you write rlog find, then it will rlog find actually provides you the gain and the pole location. So if we apply the rlog find, then you will have a cursor like that, and you can actually select the point. So if you select the point on the new root locus, which is the down one or the blue one, so we can select the location. So after selecting the location in the command prompt, basically, you are going to see what is the value of your gain K and the corresponding poles of this closed loop point. Okay, so for this root locus point. So let us look at in the MATLAB command prompt that what is the value. Okay. So now, as you can see, I already said that I know the value is 158.2 approximately. So this is what is been verified, as well as the pole locations you can select. So there is 3 pole. So one pole is at previously it was 11 point, this one was in the last class, we used the trial and error to figure out 11.61, so somewhere there. Now it is slightly changed. It is now minus 11.55. These are the 2 second order dominant poles. And the other one in between the pole and the zero, introduced pole and the zero, pole at the origin and the zero. So those two very close, even though they're very close, pole here and zero here. So their exact location is also been figured out here for that particular value of gain K. Okay, so point is what we can conclude from here is that it is not actually necessary to plot it again. Okay, so the root locus, because the change will be negligible, and with naked eyes, with empty the hand drawing, it will not be possible to distinguish. So that is why we should better leave it alone. And also we can see the final output. So whether actually we achieve a zero steady state error or not. So for that, let's go to the figure, another figure. So the other figure. Okay, so this is what you can see, the final output of both the cases. And the first one is giving you your you have 0.108 steady state error, the uncompensated one, that the blue one, and the other one, actually reddish one, that is giving you zero steady state error. So you can actually right click and look at the characteristic, and you can select here the steady state. Then it will select, give you the value. Final value for the uncompensated one is 0.892, and for the compensated one is the final value is 1. So basically zero steady state error. Now you may be asking the question that, but the compensated one is actually taking more time to getting settled. So why this thing is happening? So actually, if you look at your settling time, you look at here. This one is taking 5.15 seconds to get settled, the uncompensated one, and the compensated one is actually taking 17.8. But if you look very carefully, that actually both of them are actually getting to that initial value of 8.9 relatively at the same time. So basically, they are entering to this zone at the same time. Okay. So because of the extra effort that is been taking to reduce the error, that is why the other one is taking a bit more time to get settled and to have zero steady state error. Okay, so this is your example 9.1. We tried to take help of the MATLAB program to make it more clear how actually the steady state error is actually being vanished from our system response. Now, let us continue with our the PI controller. So now what we actually are seeing here, how it will be practically implemented. For that, we have to have a block diagram like this. So basically the error signal that is coming from here, that will be fed forward by the gain K. So we can say that this is K1 gain, as well as the error will be fed by the integral part of it. So basically you will have maybe K2 by S. Okay, so these two will be summing together. Okay, summing together to drive our plant. Okay, so this is your G of S plant. Unity feedback still, because we are discussing the cascade compensation. So this is what we are going to get. Now the point is how you are going to change this location of your zero. So pole location is not a problem. So how we are going to change the location of the zero? So for that, you can just make a simplification of this block. So this one can be considered as a single block. So if you do the calculation, that what you are going to get is GCS compensator transfer function is K1 plus K2 by S. Now if you take common, so what you are going to get is S, then K1 S plus K2. So basically take common of K1. So what we are going to get is S plus K2 by K1 divided by S. So this is your pole at the origin, and this is your the zero, nearby zero. So by tuning the value of K1 and K2, you can actually select the value of the zero. So the closer the better to the origin, but then actually angle and the magnitude contribution will be almost zero. So this is how you have to implement the PI controller. And actually in both the cases, whether you are going for PI controller or the lag compensator, actually you have to draw one root locus. You don't have to draw it again. So based on that drawing, you just do the error calculation. Now, if we go for the next segment, that is for lag compensation, because of the passive component that we are going to use, because of that passive components, it is not possible to obtain a pure zero, to obtain a pole at the origin. So it is not possible. Because of that, whenever at the end of the book we'll see the realization of the compensator, then you're going to see why it is not possible. So now we name this one as a lag compensator. Okay, so lag compensator. Okay, so how it works, it will actually give you a transfer function like this: S plus PC, S plus JC. Okay, so this is the pole, closer pole to the origin, pole very close to origin, very close to origin, and JC is 0, very close to the pole. 0, very close to the pole. Now, which one will be greater or which one will be lesser? This is what we have to derive. So whether JC value has to be greater than PC or the other one, that is what you are going to see from the derivation. Okay, so so what we are actually saying, that we have to introduce a compensator block diagram like this. Okay, so now try to derive. Let's first of all draw the block diagram, then it will be easier to deal with. So we have, without the compensation 1K, we, in this particular case, the book used type 1 system, but it's not necessary that you have to go with a type 1 system. You can also experiment with a type 0 or type 2 system. So, but they have done it. So we are also actually following the same thing. So S plus Z2 goes on. A series of zeros and then we have S, and then you have series of poles. Okay, so this is uncompensated one. And then with the compensated one, what is the difference? I'm just showing the difference block. So in the compensated one, what we have is now K. With a K, you have S plus JC. Then you have S plus EC. Okay, so the rest of the block is remaining as it is. So now let us calculate the error for both of them. So for this one, this time we have a type 1 system. So because of the type 1 system, it has to be KV, you have to calculate. So KV is limit S tends to 0, S G of S. Okay, so the whole thing is actually G of S. The forward path gain basically. So what we are going to get is K Z1 Z2 goes on divided by P1 P2 goes on. Okay, so this is your KV. So say this is old system or uncompensated one, and for the new system KVN, what we are going to get is we have limit S tends to 0, then you have S, then KS plus JC divided by S plus PC. Then you have the previous one, that is S plus J1, S plus J2 goes on. So divided by S plus P1, S plus P2. Okay. So they're getting cancelled out. So S are getting vanished. So what is left with is ZC by PC into you have a K Z1, Z2 goes on divided by P1, P2 goes on. Okay, so this is, as you can see, nothing but the previous one. So what you can see that K, KV new is going to be ZC by PC into KV old, or the uncompensated one. So KVN divided by KV old is ZC by PC. Okay, so what do we want? We want because your steady state error is basically 1 by KV, isn't it? So the new KV, we actually want it to be higher than the previous one. So, so what we want is KVN has to be greater than KV0 or KVO. Okay, so for that, what ZC by PC also has to be greater than 1, and ZC has to be actually greater than PC. What does it mean? Your PC has to be very close to the origin, and ZC has to be somewhere here, very close to the pole. Okay, so the value of ZC has to be greater than the value of PC. Okay, so this is how we cannot completely eliminate the steady state error, but we can actually eliminate the steady state error by some margin. Okay, so let us try to repeat the previous example, previous system for the one that we actually had K G of S H of S equal to K by S plus 1, S plus 2, S plus 10. That is your previous example 9.1. So we are continuing with example 9.2. Example example 9.2. So basically what they're asking you to do is 10% reduction in your steady state error. Right? So exactly the same system, open loop system, then they're asking you to have a 10% reduction. So whenever they will ask you 10% reduction, you actually have to understand that by a certain percentage always refers to lag compensator, not ideal PI controller, because PI controller will make the steady state zero. So lag compensator is our our design uh, selected compensator. So now 10% reduction. So previously, what was our error? So our previous error was 0.108. 0.108 was the previous error. So we have to have 10% reduction in the error. So that means the new error that we are going to have it has to be divided by 10. So this is 0.0108. This should be your error. And because of this, what we are going to get is error for the formula was 1 by 1 plus Kp. So which is 0.0108. So if you just try to figure out the value of the Kp after a bit of manipulation, and then you are going to see that 1 minus E infinity by E infinity is actually your value of the Kp. And if you put the value, then you are going to see that required amount of Kp is basically 91.5926. Okay, so this is your new value of Kp. So for simplicity, you can say this is new value of the Kp, and the previous value we calculated in the last class was actually 8.229. So the relation between the Kp and your Kp and your pole zero we already figured out here. Okay, so KVER you can actually using this formula, what should be the value of ZC and ZP, you can easily figure out. So ZC by ZP equal to ZC by ZP equal to KPN divided by KP0. So 91.5926 divided by, previously it was 8.229, and that is approximately 11.13. So you can see that the value of ZC has to be 11.13 times your ZP. Okay, so actually it has to be PC. Okay, so this will be your PC. Now you just now the question is how you are going to select this. So again, this is based on your experience or based on your choice. So the value of the PC has to be as close as your origin possible. So let's say that this is 0.01. Okay, so you have lots of choice, 0.1 as well, or 0.001. So whatever you prefer. So any one you can choose. So at the bottom line is, after designing the system, you have to go through the system's simulation to check whether whatever you wanted that you get or not. So we selected as the book has selected. We're not changing with them, so we are keeping in line with them. Then ZC will be 11.13 times your 0.01, and which is approximately 0.111. Okay, so we don't have to plot the root locus again, but we can actually verify our system behavior and steady state values, whether they matched or not. So you can check that. If you want, I can also show in the MATLAB. So next program that okay, so this is straight from the book. So we haven't done anything new. So we just copied it from the book. So there is another way to actually uh, plot it, not necessarily using generating the numerator denominator. You can directly give pole zero gain. I'm not sure how far you actually covered in the lab. So pole zero, using that you can directly give the pole. You don't have a pole at zero, then you can give the poles here. Then you can give the gain of the system. Okay, so if you just plot it and then look how it looks, the simulation. So now if we run it, then you're going to see that this is how it looks like. And if you try to see the steady state values, then you're going to see that this was the uncompensated one, and now it is very close within the 0.1 range. So previously was 0.1 and 10% reduced to 0.01 range. We are very close. So this is how you have to design the lag compensator. Designing is not that important. The problem here is every time you're doing the thing, you have to actually draw the root locus. Then based on that, you actually have to design the either PI controller, which is a pole at the origin, or actually the PID, sorry, the lag compensator, where actually you can reduce steady state error amount by a certain fraction. So let us go to the next segment. This is all about improving the steady state error. So our next segment. Okay, so before that, actually, you can also look at the table they have plotted. So a table like this you have to generate as well in the exam. So this is your table 9.1. Table 9.1 from the book. So where is our, okay, so this is your table 9.1. So once you know what is your gain, we know how to calculate the gain, then how to calculate the KP, all these things actually we already done. So what is new here is everything we already calculated. So this is we checked from the simulation results. Okay, so a fourth pole is being generated. Okay, so zero and the pole combination as well. Okay, so this table, you have to have a comparison table like this, more or less. And in some cases, also you have to figure out additional parameters like settling time, or peak time, something like this. So this will be more actually important in the next topic that we are going to discuss, that is improving the transient behavior. So let us go into that segment, that article. So next article that we are going to discuss is article 9.3. Okay, so article 9.3. 9.3. Improving transient behaviors, improving transient behavior via cascade compensation. So we are still with the cascade compensation. Okay. So we already said at the introduction of this chapter that this has to be done in two ways. So we have to introduce additional poles two ways. One is PD, proportional derivative controller, and the other one is a lead compensator. So we are going to see both of them. So in start with the first one. So in PD controller, basically we are going to have a pure differentiator. Okay, so both of them are actually based on the derivative design. Okay, so if it is ideal with the active components, then it is called PD controller. And if it is non-ideal or with passive components, then you call it lead compensator. So if you can introduce a pure derivative controller, that means a pure pole, that is GC S equal to S plus ZC, only pole, only zero, then it is called a PD controller. Okay, so but if you also have to introduce pole along with the zero along with the pole, then it is called actually lead compensator. So just let's start with your PD controller, how actually you can bring it. So now in your article 9.8, they actually have used different location of the zero. Then they have analyzed how the system behaves. Okay, so it is difficult to draw the whole thing. So we prefer to go into the book again, and then we'll try to see with the designing part. So article 9.3, improving transient behavior. So you have proportional plus derivative controller, as well as you have lead compensator. So we are starting with ideal derivative controller. So this is, we are just introducing 1, 0. And what we are actually trying to do here is, this is your uncompensated system. So this is how it looks like. So the existing root locus, and somehow say we are not happy with this particular point with your 4.4 your zeta. So what we want to go somewhere else. Okay, so how can we go somewhere else by changing the root locus? This is what is our ultimate target is. So they, in this particular segment, they have given 4 examples. The first example is they have bring one. So as you have seen here, we have 3 poles, 1 pole at -1, original system at -2, and at -5. Okay, so now we are introducing 1, 0. So 1, 0, 3 different figure and 3 different location of the 0. So 1, 0 here we have introduced, and in this particular case, so 0 is actually cancelling. 0 is also at -2. -2 we already had a pole, so we introduced a 0 at -2. So the pole 0 cancellation directly effective. So this what we have, the segment is right now is just in between -1 and -5, exactly at maybe 2 point in the middle. So you are going to have one vertical line going upwards and one vertical line going downwards. Okay, so and the intersection of the zeta line giving you a new point. So whether the new value of settling time new value of your peak time and the percentage overshoot, with whether we have a percentage overshoot is not going to change because we are still on the same line. So the rest of the value, whether we're happy with it or not, this is what we can check here from the final table. So this is the figure B actually. The 0 is at location -2. So in the next figure, we'll be shifting the 0 location, and then we'll try to see how it behaves. Okay, so in the next figure, now the 0 location is changed to at -3. So 0 location is changed to -3. So you have one root locus segment going from there, and these two are actually merging together, and then one is going up and one is going down. So you have new intersection point, and based on the new intersection point, this is your sigma d, and this is your omega d, and that will give you actually the values of ts 4 by sigma d, and value of your omega d will actually give you the peak time, that is pi by omega d. So this sort of value you can calculate. So we'll see one by one by taking 1 0 at -2, by taking 1 0 at -3, and in the last figure as well, by shifting it further, we are going to see. So now it is closer to, it is now at -4. So your new segment here is this one, and they are again merging together. It is identical because further you go, actually closer to the -5, it is maintaining almost similar pattern. So this is your new point, and the new point is actually giving you corresponding different values of your sigma d and omega d, and you can actually calculate new values of your settling time or peak times. Okay, so let us now compare the 0 locations and their behavior from the table. Okay, so table 9.2. So they are showing here this is uncompensated system, the first one. Then you have a 0 at -2. Then the next one is -3, and the next one is -4. So you look at their zeta value. All of them are actually having same zeta value and corresponding percentage overshoot, because we figure out the our second order poles based on the intersection. So these two values will be same; they will not change. So what is changing is your value of your omega n, and based on that, zeta omega n is actually sigma d. So this value is changing as well as this value. So now you actually have to choose which system you're happy with. So basically, the lesser the settling time, the faster it goes to the destination. So based on that, this system is is good if you are actually interested about lesser settling time. But if you are interested, similar thing also applicable here for the peak time, smaller. Okay, now look at the steady state error condition, whether it is actually improving or deteriorating after you just introduced a 0 in the system. So look at here. So look at your 0th steady state error. So okay, so uncompensated one was actually having 0.297, and then this one is giving you, because we are actually happy about these two results, but your steady state error compared to the other ones, this is actually giving you smallest value. Okay, so we are actually happy about, we are more happy about this value. So this is how you have to choose which results is more important to you, whether faster response or reasonable values here with a smaller number of steady state value. So this is what you have to do, figure out. So now I think you already know how to figure out the value of zeta. So this is your uh, sigma d. Sigma d is nothing but your zeta omega n, and this is your omega d. So omega d is nothing but omega n root over 1 minus zeta square. So omega n root over 1 minus zeta square. So if you just compare these two values, from this one you can easily find out what should be the value of zeta as well as what should be the value of omega n. We already know the value of the zeta because based on that zeta we calculated, or basically based on some certain percentage of overshoot we calculated. So zeta is known, you can easily find out what should be the value of omega n. So once you know that, rest of the things should not be difficult to calculate. So forming a table like this should not be that difficult. Okay, so this is we have just seen that how we can introduce zero in different location, and based on that how your root locus changes. And now have a look at their responses as well. So their response is something like this. Okay, so uncompensated one is this one. Okay, so and the rest of them are very close to actually very close to zero steady state error, even though it is not zero. So very small values of steady state error is there, and you can check which one is having lower peak time, which one is having setting time is higher. Okay, higher or lower, so you can verify that. So someone was asking about whether the intersection point is an approximation. Yes, so once you are using the programming uh, platform like MATLAB, you can actually precisely figure out the point. But once you're drawing by hand and in the graph paper, it is always an approximation. So you have to approximate. That is why we, in the first point, we said that why it is not necessary to draw a second figure in case of the steady state error design, because there will be almost similar location. Okay, so I hope I answered it. The answer is the question has been answered. So now, so as you can see here, the different location, you have different zeros, and that zero location is changing your response curve a bit, and as the table suggested, this one will be giving in most cases the best result, even though the steady state error is slightly deteriorated, but 0 at -2 is giving best result because of the fact that it is actually cancelling the pole 0, so your system order is also changing. Okay, so rest of them is also being shown here, and accordingly you have to choose the location. So let us not spend more time on analyzing this, rather let us try to look at the problem. So problem 9.3, what it says that a block diagram given, and you have to design an ideal derivative compensator, so which is actually PD controller, so to yield a 16% overshoot with a threefold reduction in settling time. So what does it means is basically percentage overshoot line is given. You have open loop block diagram, open loop transfer function is also known. So you can draw the root locus. So they will never say, like, look at the question. They're not saying that you draw the root locus first, but it is inherently you have to do it, because otherwise you can proceed further. So you have to plot the root locus, and then you have to find out 16% overshoot line. And once you do that, based on the idea of your chapter 8, then you can figure out the intersection point. So once you have your intersection point, from there on, you actually have to design your derivative compensator. So basically, we are repeating chapter 4. Okay, so chapter 8. Then we are plotting this root locus. So initially, we had pole here, here, and here. So then this is your real axis segment, one of the real axis segment. The other one merges together to the breakaway point, and then this is your 16% overshoot line. And then you have to find out this intersection point. So you have to do this one as well as the gain value. You have to calculate finding the distance between the poles from that particular location. So after doing all this, then we actually go, which is part of chapter 8. Then actually we go proceed to the design. Okay, so we also start from here. That our intersection point is minus 1.203 plus j 2.04. Okay, so from here, let's start solving. So what it asks you to actually design a uh, PD controller. So you have to design the PD controller that will give you 1/3 of your existing settling time. So what is your current settling time? So settling time is basically nothing but minus so 4 by sigma d. Okay, so 4 by sigma d. So 4 by sigma d will give you a 4 by sigma d is this value minus you can omit the negative sign 1.025. So 1.025 will give you approximately 3.320. So this is existing value of your settling time. So what they're asking you to make it 1/3. So your new settling time new has to be 3.320 divided by 3. That is approximately 1.107. Okay, so this is what you have to have. Now, based on this settling time, you can actually find out the real portion of your 0. Okay, so how can we find out the real portion of your pole? Say we are somewhere here. So we can find out the real portion of your, that means sigma d, we can calculate. Then we also have to find out the location of omega d. So sigma is 4 by TSN. So 4 by TSN will give you 4 by 1.107. 1.107, which is 3.613. So we know that our location should be somewhere here. So because 3.6, so this is your real axis segment, somewhere here, minus 3.613. Now the height we have to find out. So for calculating the height, it's not that difficult because so far what we are doing here is we are always finding that tan angle, isn't it? Tan this angle, because it has to be same zeta ratio. So tan 120.26 degree should be equal to your height by base. Base we already calculated 3.619. So 3.613 is your base, and then this is your height. Height is nothing but omega d. So omega d should be equal to 3.613 tan 120.26, and which will give you 6.193. So you are having some point here. Okay, so just so what we figured out so far is the real axis segment is minus 3.613, and your, so what is your pole location should be then minus 3.613 plus minus j omega d, that is 6.193. So somewhere here maybe a bit high. So somewhere here you're going to have your pole that has to be in line with that one as well. So it's difficult to plot it here. So bottom line is we can find out the point. So once you know the point minus j minus 3.613 plus minus j 6.193, then actually you have to find out the angle contribution of the poles and the zeros of the existing system to that particular point. Okay, so what we have figured out so far is for the new system, we figure out that our point has to be at minus 3.613 plus minus j 6.193. Okay, so once we know the point and we know the open loop poles and zeros are actually at s equal to 0, s equal to 4 and s minus 4 and s equal to minus 6. So this is what we already know. So we can easily find out the angle contribution by these poles to this location. Okay, so the angle contribution is, and since all the angles are actually pole angles, all of them will be negative. So tan inverse height by base. So height is always same 6.193 divided by the base. So for this one, the base will be same as this one. So 3.619. Okay. So one thing you have to be careful, since we are actually plotting the angles. So we have to be careful about the angles as well. So 3 somewhere around 3.6 and then 6 somewhere here. Say. So the angle from the origin will actually have this angle. So it has to be 180 degree minus that value. So that is why if you don't draw the figure, it will be difficult for you. But it is a pole angle more or less, so it will be negative. Then what about the rest of the angle? The rest of the angle has a base value higher than that particular point. So basically the angle will be something like this. Okay, so this angle you can directly apply the tan inverse formula. So tan inverse for the next one set 4, what we are going to see is height is always same 6.193 divided by 4 minus 3.613 minus you have tan inverse 6.193 6 minus 3.613. Okay, so if you find out the summation of all the angles, then you're going to see that minus 275.6 degrees that you are going to get. But we know that for any point to be on the root locus, for any point to be on the root locus, the angle contribution has to be odd multiple of 180 degrees. So if we see that if we can add plus 95.6 degrees, then we can go to odd multiple of 180 degrees, isn't it? So basically the zero that we have to introduce for the compensator, that has to contribute 95.6 degrees. Okay, so 95.6 degrees and angle is more than 90 degrees. So whenever the angle is more than 90 degrees, you will always have to apply the 180 degree minus that formula. So tan 180 degree minus 95.6 should give you the height and the base. So height we already know. Height is basically the same as before. So that is 6.193. And what is the base? Base is basically difference between the location of the pole or the zero and the point in consideration. So basically you can say that it can be something like this, 3.613 minus sigma. So we are more interested about finding the sigma, where the zero location should be. Okay, so if you plot the values now, then what you are going to get is sigma value will be negative 3.006. So what does it mean? We have to introduce a pole or introduce a compensator 0 here, approximately here. Then the contribution of this one will be almost 95%. 95.6 degrees, and because of that, this new point will be on the root locus. Now again the question comes whether you have to plot the root locus again. Plot the root locus again. Okay, so the answer is this time actually you have to do it because of the fact that we are introducing 1 0, and because of that your direction of your root locus will be changed. Okay, so this one will be going from this one to this one, and these two will be merging together, and then they will somehow follow a path like this, and eventually it will be going through that point. Okay, so this is why in case of adjusting the improving the transient behavior, whatever according to your desired specification, actually you have to go through two root locus. One root locus for finding out the point, existing point, and from the existing point you have to figure out what is the new point, and from based on the new point you have to find out the location of the 0, as we have figured out here. And once you have figured out the 0, then you have to again draw the root locus to where it has to be approximately. So don't necessarily it has to be very precise, but you have to draw it and just to check. So PD controller that we have studied. So the configuration of this one will be something like this. You will have the proportional, okay, and then you have the derivative. So say this is your K1, this is your K2S, and then you sum them together. Then it will going to drive your plant GPS. Okay, so what should be the GCS? GCS will be K2S plus K1. So basically take common of the K2, so S plus K1 by K2. Bottom line is same, change the value of K1 and K2 to find out the location at 3.006. Okay, so this is how you actually have to draw the designing and implementation of your PD controller to achieve 1/3 of the previous settling time.